Okay, welcome back. We're working at 10.4 now. We want to add, subtract, and divide rational expressions. Or radical, again, so used to saying rational. Okay, so first we'll deal with addition and subtraction. And addition and subtraction is pretty easy. You're just thinking of it like combining like terms. So if they have the same kind of radical, it's like having the same variable, and you could add the coefficients. Okay? So recall that phenomena back in your pre-algebra. If you have 17x plus 3x, you just add the coefficients together, so you get 20x. Okay? So now, how is this similar? Well, you may have something like 17 radical 2 plus 3 radical 2. And to add them, all you have to do is add 17 plus 3, and you get 20 radical 2. Okay? So not really anything new, not ground shaking at all. Let's take a look at number 4. We have 9 times the cube root of 7 minus 4 times the cube root of 7. Okay. So 9 minus 4, of course, is 5. And then we have the cube root of 7. It's pretty easy. Let's look at maybe number 10. I have 6 square root 7 minus the cube root of x plus 2 square root 7 plus 5 cube root of x. Okay. So these guys have the same radical, and these guys have the same radical, so you have to combine those pairs. 6 radical 7 plus 2 radical 7s is 8 radical 7s. And then negative 1 radical cube root x plus 5 cube root x is going to give you 4 cube root x's. Okay. And then you can't combine those because they don't have the same radical. Okay. So those are easy because they're kind of already simplified, but they're going to throw some at you that aren't. So this is kind of the same topic, but here you have to do an extra step of simplification. Okay, so simplify first. And number 14 is where we'll start. We have 5 radical 12 plus radical 75. Okay. And I want to simplify, so you're marching perfect squares out the front door. So 5 times radical 4 times 3 plus the square root of 25 times 3. And then you can march the 2 out the front. And, because this is 5 times radical 12, and you march the 2 out front, it'll be 5 times 2. Okay, so that'll give you a 10 in front, and you're left with radical 3. And then with this guy in the front, you march out the 25, you'll have a 5 in front, and then a radical 3. And then they're like terms, so you can combine the numerators, or combine the coefficients. 10 plus 5 is 15. Keep moving. So we have number 18 here. 3 cube root 24 plus cube root 81. Same game. We want to simplify first. So I have 3 times the cube root, and that's 8 times 4. Yeah, no, 8 times 3, sorry. And then plus the cube root of 27 times 3. So I could, in this guy, I can march out the cube root of 8 is 2, so that would be 3 times 2 is 6, times the cube root of 3, plus the cube root of 27 is 3, times the cube root of 3. 6 plus 3 is 9, and then times the cube root of 3, and that's it. So I get 22. I have the cube root of 24xy cubed plus y times the cube root of 81x. So very similar to the last one. I'm going to factor. So this will be 8 times 3 times x times y cubed. The perfect squares are right here and right here. I can march them both out the front. Plus y times the cube root of 27 times 3 times x. Okay, the cube root of 8 is 2. The cube root of y cubed is y. And then I have the cube root of 3x. And then plus, here I can march out the 27. So that would be 3y. And then times the cube root of 3x. So these are like terms, and you can add them together. And actually, you can consider this whole part as the variable. Okay? So it's 2 of these plus 3 of these. You end up with 5 of them. Let's look at one more and go on to the next topic. So I have the square root of 4x minus 12. Plus the, equals, plus the square root of x minus 3. So first, the first guy I can march out a 4. So you factor the 4 out, you get x minus 3. And then plus square root of x minus 3. Square root of 4 is 2. And then square root x minus 3. Plus square root x minus 3. So there's 2 of these and 1 of these. That gives you 3 of them. So you have 3 square root x minus 3's. Okay, so we did, what did we do? We did, I'm running out of paper, obviously. We did addition and subtraction. Now we want to do some division. Okay, so section 3 now. We're working with division. And in particular, now we have another kind of rule like the product rule from before. And of course, it's called now the quotient rule. So it's the same idea. If you have, before if we had a product, we could, of 2 things on our radical, we can make it a product of radicals. Now if we have a radical of a quotient of 2 things, we can make it a quotient of 2 radicals. Okay, so you could split up the radical into the nth root of a all over the nth root of b. And again, you could go back and forth whichever way you want to go. Okay. So that'll help us to simplify these roots of fractions. For example, the cube root here of 11/64. Okay, I can rewrite that as the cube root of 11 all over the cube root of 64. Cube root of 11 I can't simplify, but the cube root of 64, that's just 4. Okay. And that's it. Let's look at, let's see how many more we got. About 7 more. They get more and more complicated as we go. This is 36. We have 50x cubed all over 81y to the 8th. Okay. You always kind of want to simplify these things before you get carried away. I think that's a good idea, but here I don't think there's going to be any simplification to worry about. We'll just split it up into 2 roots. Whoops. So I have this equal to, split up in the square roots. This is the square root of 50x cubed all over the square root of 81y to the 8th. I need to factor this guy to march out the perfect square. So this is 25 times 2 times x squared times x. And then downstairs, those are all perfect squares. So 81, the square root of 81 is 9. And then this exponent is divisible by 2, so that'll leave me with y to the 4th. Upstairs, simplifying now, the square root of 25 is 5. So I can march this guy out and this guy out. The square root of x squared is just x, and then I'm left with 2x, and that's all over 9y to the 4th. Find some paper here. 40. Okay. So here I have the cube root of, and this paper is kind of writing all of it. So let me use more paper. This should be interesting. I found some. Yay. Sorry about that. So anyways, 40, we have the cube root of 81, x to the 8th, all over 8y to the 15th. Okay. So I can kind of start thinking about marching out perfect cubes. 81 is 27 times 3, and then times, I need some exponent divisible by 3, the largest one possible. So x to the 6 times x to the 2. Okay. And all over 8y to the 15th. So those are all perfect cubes there. And of course we want to split the cube root up into 2 parts here. One for the top and one for the bottom. So up top I can march out the 27 and the x to the 6. That'll give me 3x. 6 divided by 3 is 2. And then times the cube root of 3x squared. That's all over. 2 cubed is 8, so 2. And then y to the 15 divided by 3 is 5. It's 44. We have the 5th root of 64x to the 14th all over y to the 15th. So I need perfect fifths. 2 times 2 is 4, 8, 16, 32. So 2 to the 5th is 32. And of course I want to split up the fraction into 2 roots. I keep forgetting that. 32 times 2x to the 10th times x to the 4th. Again, I need an exponent divisible by 5, the largest one possible. And then downstairs, y to the 15th is a perfect fifth. Anyway, so I'll end up with, I can move this guy, and this guy out. And I have 2x squared times the 5th root of 2x to the 4th all over y cubed. So I got 48. This time we're kind of going in the reverse direction. I have the cube root of 54 all over the cube root of 2. I could split that, turn that into one big fraction, 54 all over 2. 54 divided by 2 is 27. Okay, so now I can go ahead and take the cube root of that. That'll be 3. These last couple are the same kind of idea. So 52, I have the square root of x to the 7th, y to the 6, all over the square root of x cubed, y squared. Okay. So turning that into one big root, I'll have x to the 7th, y to the 6, all over x cubed, y squared. Simplifying, so you're subtracting exponents when you do division. x to the 7 over x to the 3 is x to the 7 minus 3, which is x to the 4th. This one will be 6 minus 2, so y to the 4th. And then both of those are perfect squares, so you just divide their exponents by 2, end up with x squared, y squared. 2 more. There's 56. I have the square root of 54a to the 7th b to the 11th. So this will be the square root of, there's a 9 in there, right? So 9 times 6 times a to the 6, a to the 1, times b to the 10th, b to the 1. Sorry, I had to smush that in there. So these guys are the perfect squares. I have 3a third b 5 times the square root of 6ab. I guess I forgot to put the denominator in there. Sorry, so that wasn't 56. That was part of 56, apparently. 56 is the square root of 54a to the 7th, b to the 11th, all over the square root of 3a to the negative 4th, b to the negative 2. Okay, so rewrite it as one root. 54 divided by 3 is going to give you, well, I don't know. That's what 54 divided by 3. 1, 3, 24, 18. And then a to the 7th over a to the negative 4, you subtract the exponent. 7 minus negative 4 will give you 8, 7, 8, 9, 10, 11. b to the 11th minus negative 2 will give you 13. Okay, and then we could simplify. So this would be the square root of 9 times 2 times a to the 10th times a to the 1th times b to the 12th times b. That'll be 3a to the 5th, b to the 6th times the square root of 2. So we pulled out this guy, and this guy. 2, a, b, and then that's it. One more. So we have the 5th root of 96 x to the 12th, y to the 11th, all over the 5th root of 3x squared, y to the negative 2. Okay, so again, we just simplify. 96 divided by 3 is 32, I believe. X to the 12th over x squared, so subtract exponents, x to the 10. Subtract exponents again. 11 minus negative 2 is y to the 13th. And then 32 is a perfect fifth, that's just 2. And then I can pull out the x to the 10 is x to the 2. And then, of course, I'm left with the 5th root of y to the 13th. Y to the 13th is y to the 10 times y cubed. So I can pull out then the y to the 10th. So 2x squared y to the 2. And then the 5th root of y cubed. Okay, that'd be it.